welcome to the introductory course of probability and random variables and random processes. This course is designated as 490H this year, only up to this year. From next year, it will be changed to EECE302, which is a mandatory course. It's okay this year, it's elective. Okay? You can anytime drop and change to some math course, which is also acceptable for your graduation. Anyway, so what is this class? This class is all about probability. And why you need this one, by the way. So today I'm going to focus on why you need to take this course. Because that will motivate you to study this one. Okay, so here comes the most important statement I want to give you. In electrical engineering, we often encounter unavoidable uncertainties. And to handle these uncertainties, we need a theory of a probability. And what kind of electrical engineering subjects require this knowledge? First, communications and networking, computer networks or some communication networks. Also, signal processing, video, audio, acoustic, control and robotics, and also low power, high speed electronics. And radar engineering, you want to detect whether the enemy plane is coming or not. In semiconductors and circuits, optics, so almost every area of electrical engineering requires this knowledge. Of course, the depth or width of the knowledge required in each subject varies. Okay? For example, in low power, high speed electronics, you may need very little knowledge on probability. But in signal processing, control, robotics, communications, networking, if you are not good at in this subject, you'd better move to other subjects which less use this probability. What I found from my experience is that some students find this subject very, very difficult, even though he or she has been a top student. So it seems that there are some reasons why some people are very weak in this subject. So if you find this subject is the one, then you need to seriously reconsider your career change. But what I want to emphasize is this one. You must study very hard before you give up. The only way whether this course or this study on probability does not match you, the only way to find is to study very hard. I guarantee that if you do not study very hard, you will definitely feel that this course is very difficult. But this course may be the one that you can do it best among your friends if you study very hard. So whenever I consult undergraduate students, I emphasize that you have to study very hard in order to identify which course matches you or which course does not match you. Many undergraduate students, when they go to graduate school, they have very less information about the lab they join. I may ask some graduate students who are sitting in if they have some knowledge about what's going on in their lab. Probably they say that I have almost no information. How can you know the depth of that knowledge required in the lab before you join? So many students just join a lab, go to a graduate student based on their some feeling, okay? Not based on solid some statistical result. For example, you study very hard throughout undergraduate years and find that even though you did your best, you are not good at in signalization systems and probability, control, digital communications. Never join my lab. Never join Professor Pugyan Bak's lab. Okay? That's the way you increase the probability of your career success. But if you do not study very hard, you don't know whether you can do very good at that subject or not. So your probability of career success becomes very low compared to the other case. Okay? So anyway, try your best to be good at in this course. And that will really pay you off. especially when you choose your lab for your graduate study. Anyway, then what uncertainties we need to deal with? Okay? In electrical engineering, we only have signals and systems. Okay? So there are uncertainties in signals, and sometimes there are some uncertainties in systems. In order to remind you what is the signal and what is the system, let me give you some idea. Some students often ask, what's the difference between signal processing, communications, and control? They are almost the same. These subjects are highly based on mathematical tools. So you don't need math, you don't love mathematics, you'd better not to choose these subjects. This here comes most important block diagrams that shows you the difference among these very similar subjects. So these are given blocks, which means that when you are given some signal processing problem, you are usually given a source and a sink. And what you are asked to do is to design what? Design some system that has input and output connecting the source and sink. And this is called signal processing. In this case, usually source is a random source. So the signal generated by the source contains some uncertainty. And this may be caused by some uncertainty in the source. In communications, we have three blocks: source, channel, and sink. And what you want to do is to convey the information generated by source with almost zero or very small probability of error to sink. But you are subject to use this channel. In that case, you design two blocks. One is called encoder, and the other is called decoder. And what you want to do is to jointly design this encoder-decoder pair to, for example, maximize the transmission rate between source and sink, at the same time to minimize the probability of data error. Now, what is the control? Control, this is maybe oversimplified block diagram, but in control, you have some system and you have some sink. What you want to do is to design some system that is called controller that generates some signal so that the output of this system becomes some desirable signal. For example, the output exactly follows what a curve we want to generate, something like that. And here, these arrows represent the flow of signals, and these signals may contain some uncertainties due to, for example, in airplane system, air turbulence, some defects in your circuits. In communication system, you have random mapping inside this channel, so you have some uncertainties. You have to fight with these uncertainties as an electrical engineer, but you don't know nothing. Then your system will perform very poorly. So this course is kind of to prepare you to fight with uncertainties in signals and systems, so that you can be a better warrior. Okay? Now, let's go back to our note. As you learned in signals and systems, there are some mathematical entities often used in modeling electrical signals. First one is a scalar, like a real number, complex number. Second one is a vector, as you learned in high school math, an ordered collection of, for example, real numbers. You can rearrange this one to a matrix sometimes. Sometimes you use a sequence to model an electrical signal. For example, a discrete time signal, as you learned in signals and systems. By the way, the course Signalization Systems is the prerequisite for this course, which means it is required to take this course. So if you haven't yet taken Signalization Systems, or you have failed in the course, not to take this course, I guarantee that you will have another fail. Because after almost half of this semester, we will learn a lot of results from the Signalization Systems, like first, convolution. If you have no idea about convolution, what can you do? We will also use Fourier transform. You don't know anything about Fourier transform, you cannot take this course. And around at 3/4 of this semester, we will intensively use linear time invariant systems to process random signals. If you have no idea about linear time invariant system, what can you do? Okay. So the prerequisite of this course is Signalization Systems, and it is very important. I find some students, some undergraduate and graduate students, taking some courses, and they complain that the professors do not explain some concepts in detail enough. But usually they do not look at the syllabus of the course. The syllabus usually clearly states that some subjects are prerequisites, which means professors will not introduce the notions again. Anyway, sometimes you use a waveform, a time function to model an electrical signal. Sometimes we use a scalar field or vector field, and sometimes, as you learned in what? Electromagnetics. Right? Potential fields or electric fields. But sometimes these signals contain uncertainties. Then we have counterparts. To model some electrical signal, which is definitely a scalar, but containing some random, some uncertainty, then we introduce the notion of random variable. What is the counterpart? You can guess. A random vector, random matrix, random sequence, or sequence of random variables, random process, a random field. And there are other mathematical entities you never learned in your undergraduate study, but there are many. Okay? There are some mathematical entities quite often used in modeling some electrical signals, but you never learned. Maybe there are some gold mine there for you to discover one of the most important results in electrical engineering during your graduate study. So usually in this introductory first lecture, I recommend you to take more mathematical courses, more math courses. Okay? For example, mathematical analysis course, which is all about sequences, convergences. That is very, very important subject for your success in the graduate study. But undergraduate students rarely take that course, and they find that they are not well prepared. Don't do that. Don't repeat the failure of your senior students. Okay? Now, uncertainties in systems. As I already drawn here, sometimes the source has some uncertainty in generating the signal. Sometimes channel introduces uncertainty. Sometimes system itself introduces uncertainty in control. What about other applications of this probability theory? Probably some of you are just sitting here in this classroom to see what's going on in this lecture. Probably you even didn't sign up your name in the roster and you want to just watch, or you have already determined to drop this course because of my, I should be careful, right? You know that how hard I push the students in the lectures. So I want to give you some big picture. Probability theory is not just useful for electrical engineers. It is more and more intensively used in almost every interesting areas of academia. For example, statistics. Why is this important? For example, if you want to sell some product, what you usually do is to accumulate data and analyze the pattern of the customers based on probability theory. Then you want to make the optimal decision, which product to be shown in the first shelf, second shelf, something like that. In physics, definitely quantum mechanics needs knowledge of probability because the Schrodinger's equation is all about the probability distribution of the particle. Solid state physics, you may say that, why do I need that? Actually, solid state physics is based on quantum mechanics. And its energy band and band gap, all about these solid state stuffs are related to probability theory. Statistical physics, probably you have no knowledge, but this is also very important. And in economics, probably some of you want to change your career from electrical engineer to some quant or finance engineer. You need probability theory because optimal decision in stock market investment requires the knowledge of probability because you want to minimize the risk or maximize the expected revenue. Okay? Here, expected means some statistical average. Game theory, which is also very important in bargaining, business management, and one of the most difficult subjects to the master students in business management is a time series analysis because they have no idea about sequence, and especially random sequence. But we are going to learn that. So if you have some plan to just graduate this school and join some company and go for some master's degree in business management, you will someday end up in a time series analysis course and will remember what I just told you. Okay? Optimal decision, this is the most important one. Okay? Planning in your life. Also, in computer science, this probability theory is the core. Okay? In computer vision, in speech recognition, computer network, how the computer virus spreads over the net, to model that, you need the theory of probability. Machine learning, artificial intelligence, all based on probability. Is it amazing or not? Anyway, let me give you some list of what you need to learn through this course then. There are a lot, okay? So you may be frustrated, but here goes. First, you need to know what is a random experiment, what is a trial, and what is the outcome of a random experiment. And to model a random experiment mathematically, we introduce the notion of probability space, which consists of sample space, event space, and probability measure. And we will also learn about the statistical independence and independent events. And here comes the most important stuff you should never forget. Okay? For example, after 10 years, you and I meet in some place in Korea. And for example, you come and, hello professor, I was a student in your public course. Then what will be my greetings? Okay, what is the most important three things you learned in my course? I will ask you. Okay? So if you do not remember these three, I will give you a punch. Okay? Never say that you have taken my course without remembering this one. Okay? These three tools are the tools you need to manipulate some probability stuff. To compute the probability of some events, you need these three. First, the definition of conditional probability, total probability theory, and Bayes theory. Okay? So probably I will ask you again about these three, okay, at the end of the semester in the final exam. Okay? If you do not remember, probably I'll be disappointed, which means you need to retake this course. Okay, next year. By the way, after we study this probability stuff, we will introduce a notion of random variable. What is a random variable? It is some counterpart to a scalar signal. Okay? Actually, in Signalization Systems, we rarely mention a scalar to model an electrical signal. It is not because it's less important. It is because it's so obvious. You learned this type of signal throughout your elementary, middle, high school days. You know what is scalar. But unfortunately, after this one, you need to know what is a random vector. If you have taken my Signalization Systems course, probably you remember that I emphasize half of the Signalization Systems course is not taught in Signalization Systems, but taught in linear algebra course. Actually, I personally believe linear algebra is more important than Signalization Systems course. If you don't agree, write some article on why my claim is wrong. I definitely I can explain more of why my claim is correct than yours. Anyway, you need to know some definitions of cumulative distribution function, probability density, conditional CDF, conditional PDF, expectation, characteristic function. This is related to the Fourier transform. And if you take some other courses in our school, probably in that course you will probably not encounter this characteristic function. That's what I heard from your senior students. But this is very, very important. And moment generating function, and some very important distribution functions, which includes Gaussian or normal, as you learned in your high school statistics course. For random vector, we have almost the parallel notions of joint CDF, joint PDF, conditional CDF, PDF, independence, expectation, joint characteristic, and joint moment generating function, joint Gaussian. This is one of the most important distribution, and transformation of a random vector. To model a discrete time or continuous time signal with uncertainty, we need a notion of random process. And here comes some important definitions: sample path, stationarity, and ergodicity. And here are also important one, because whenever we deal with a sequence, okay, here comes sequence, we have to check whether it converges or not. And if it converges, in what sense it converges? There are 4 important modes of convergence in random sequence. First one is the convergence in almost sure sense, convergence in the pth mean, convergence in probability, convergence in distribution. And there are some special cases for these 4 modes. You have to remember strong law of large numbers, weak law of large numbers, and central limit theorem. About central limit theorem, you've already learned in your high school statistics. And for special case, there are discrete time and continuous time processes. And for this, as you learned, as you did in Signalization Systems, we have 2 approaches. One is in the time domain, the other is in the frequency domain. So in the time domain, the most important notion is an auto or cross correlation function. And the frequency domain, you need the notion of power spectral density. And here comes the linear time invariant filtering of a random process. And finally, you will learn what kind of time or spectral characteristic real valued bandpass random process have. This is very important for the students who wants to do some graduate research on communications. And after you take this course, it's not the end of your journey in this area. Okay? You need to take more to enhance your knowledge on probability theory. So here comes some related courses. For example, in electrical engineering, information theory is very important and very closely related to the probability theory. Information theory is a branch of probability theory which is used in communications, signal processing, control, and others, even in radar engineering. Of course, digital communication theory. Probably you have no idea what's the key subject, what is the kind of required one to study communications. It's Signalization Systems and probably. I draw this figure a lot of times to visualize what you do through the university. Okay? So what is the most important one? Important subject you take? Calculus. Then what is the second layer in your foundation? Linear algebra. And of course, this is kind of the figure for the systems engineer in electrical engineering. What will be these two columns? One is definitely Signalization Systems. What will be the other? This course. Okay? And then, depending on what you want to do, you may have a little bit different layers, but usually what you have is estimation and detection theory in the graduate school. Okay, so up to here, of course, some of the probability stuff must be relearned in graduate school, and here comes optimization, which is very important because every engineering problem is about optimization. If you want to build a bridge as a civil engineer, if you use all the steel material in the earth, you may build a very, very solid, strong bridge. But that's not what your boss wants. Your boss wants you to design an inexpensive but safe enough bridge within some time period. So it's all about optimization. And this kind of the CAP part may be different. You need some other signal processing courses, some communications, information theory, sometimes optimal control. But never forget about this. Okay? Maybe you want some more columns, okay? Because two columns are very two-dimensional. So you may need some more, at least two more columns. Okay? And this could be real analysis. Okay? This could be some other. For example, graph theory, okay? Discrete mathematics. So far, I hastily covered what you are going to study and the subjects you will take in the graduate courses. But what are some math-related courses? There are some optimization courses which is not offered in our department, but offered by other departments like industrial engineering. Okay. Some nonlinear optimization, discrete optimization courses are offered by professors in industrial engineering. Take that. Graph theory, you know, the math department offers this course. Combinatorics, as I told you, mathematical analysis. There are some graduate level courses called measure theory. Actually, probability theory is a subset, okay, or a special case of measure theory. So measure theory is a kind of unifying theory that includes probability theory and some functional analysis and others. And of course, there are some probability courses which requires much more rigor in handling mathematical entities than in this course.